Welcome to The Explainer. Today we're embarking on a pretty fascinating quest for precision. We're going to figure out exactly how we measure the microscopic world. We interact with precisely engineered materials every single day, but we rarely stop to ask, how did humanity actually develop the tools to see and measure way beyond the physical limits of our own eyesight?
So let's just dive right into this explainer by asking a simple question. How do we actually measure the exact thickness of a single sheet of glass? Or, say, the volume of a tiny lead shot? Imagine trying to find the exact diameter of a single, super thin strand of wire. That standard plastic ruler sitting on your desk? Yeah, that's definitely not going to cut it. The millimeter lines printed on that ruler are probably thicker than the object you're trying to measure. So we need something far superior.
Enter our absolute hero of precision, the micrometer screw gauge. It's an ingenious little instrument. It consists of a solid, U-shaped frame at the bottom. Attached to one arm is this hollow cylinder carrying a fixed pitch scale, and over that cylinder there's a rotating sleeve carrying the head scale. Finally, over on the left side, we have the plane surfaces, those flat little studs where we carefully place the tiny objects we're actually trying to measure.
Here's our quick roadmap for today's explainer. We're going to look at the quest for precision, the anatomy of the gauge, how to calculate the least count, mastering the zero error, walking through a real lab experiment, and finally, looking at our final calculations and results. Let's get right to it.
Section 1. The quest for precision. Specifically, tackling the problem of the small.
Moving right along to Section 2, Anatomy of the Gauge, which is all about screws and nuts.
Now, this complex-looking tool actually relies on a really beautiful everyday principle, just a simple screw and a nut. But to understand how this helps us measure stuff, we have to define a key mechanical term, and that is pitch. Pitch is simply the distance covered by the tip of the screw for one full rotation of the head. Just think about twisting a nut onto a bolt. The pitch is exactly how far that screw travels forward in a straight line with one complete 360-degree turn of your hand.
The mechanics here are brilliantly simple. By giving the screw head a specific number of turns, we can accurately measure the linear distance it covers on that pitch scale. See, by rotating the outer sleeve, we're pushing the screw forward. The real genius here is that the instrument transforms rotational movement, which is super easy for our clumsy human fingers to control, into highly precise microscopic linear movement. It's kind of like magic, but it's just great engineering. That brings us to Section 3, calculating the least count. Or as I like to call it, the gauge's ultimate superpower.
So to find this instrument's absolute minimum measuring threshold, we use a really simple but profound little division formula. Looking at our lab notes, the least count equals the pitch divided by the number of divisions on the head scale. By taking our pitch and dividing it by the 100 tiny hash marks carved all the way around that head scale, we can accurately measure incredibly small fractions of a distance.
To put that into perspective, using the specific gauge from our lab report, the pitch is 1 millimeter, and there are 100 divisions. Doing the math, that gives us a least count of 0.01 millimeters. That is an incredibly precise threshold. Literally, every single time you turn that head scale by just one tiny hash mark, the gap between the studs closes by exactly 1/100th of a millimeter.
All right, Section 4, Mastering the Zero Error. Every hero has a flaw, right?
And every great instrument has its quirks. Figuring out the zero error is a completely vital calibration step because of manufacturing variations or honestly just everyday wear and tear. When you close those flat surfaces completely, the scales might not perfectly align at zero. When you look at the examples from our lab notes, you can see a no error situation with a 0 hash mark on the circular scale lines up perfectly with the main barrel. But in the other scenarios, sometimes the 0 stops a bit below the line, and sometimes it rotates a little bit past the line.
We absolutely have to correct for this. If the 0 sits below the reference line when the gap is fully closed, the instrument essentially has a built-in gap. We call that a positive error, which means your final reading is going to be slightly too big. So your mathematical correction has to be negative to fix it. On the flip side, if the 0 crosses the baseline, the instrument is reading too small. That's a negative error requiring a positive correction. You simply add or subtract the number of hash marks it's off by and multiply that by your least count.
Moving to Section 5, the lab experiment walkthrough. Let's start our mission.
With all that mechanical calibration out of the way, let's actually use these handwritten lab notes as our field evidence. We're going to use this master formula for our combined reading. Here's how it works in practice. When you clap an object in the gauge, you first read the main solid number exposed on the inner barrel. That is your PSR. Then, you look really closely at exactly which tiny hash mark on the rotating sleeve perfectly lines up with the center line. That's your CHD. You multiply that by 0.01, add it all together, apply your zero correction if you have one, and boom, you have your microscopic measurement.
Reviewing the meticulously tabulated data from this lab report, we can see the students successfully extracted the mean thicknesses and diameters for a few test subjects. And notice they took multiple readings to find a reliable average, always a best practice in the lab. The glass plate's thickness came out to 4.9 millimeters. The metal plate, incredibly thin at just 0.27 millimeters. The wire's diameter is a minuscule 0.53 millimeters, and the sphere's diameter measured exactly 6.32 millimeters.
Which brings us to our final section, Section 6, Final Calculations and Results. Let's look at the proof.
Now, finding the exact diameter of a tiny wire is a great party trick, sure. But using that precise number to calculate the exact volume of material, that is the absolute foundation of modern manufacturing. Dramatically, the volume of our wire is revealed through the math to be a totally microscopic 0.0198 cubic centimeters. By taking our wire's diameter of 0.53 millimeters and running it through the cylindrical volume formula from the lab notes, we are quantifying an amount of physical space that is barely even visible to the human eye. And similarly, the volume of the little lead-shot sphere is cleanly calculated at an exact 0.132 cubic centimeters, using the formula pi times diameter cubed divided by 6, and plugging in our meticulously captured mean diameter of 6.32 millimeters, well, we get a flawlessly precise volumetric result. It's pretty amazing when you think about it.
As we wrap up this explainer, I really want you to consider how mastering the measurement of the unmeasurably small makes practically every piece of modern engineering you rely on possible. From the microchips powering the very device you're using to watch this right now, to the aerospace components keeping giant planes in the sky, it all traces back to the ingenious mechanics of tools exactly like the micrometer screw gauge. So what other invisible dimensions shape the manufactured world around you? Keep questioning, keep measuring, and I'll catch you in the next explainer.